Using the same approach that we solved linear systems with substitution, we can also solve nonlinear systems with substitution. The procedure is basically the same, but the only difference that you need to be aware of is that you may come up with more than one solution for a nonlinear system, where you just get one solution for a linear system. So let's quickly go through this process. Just like we did for linear systems, the first step in solving a nonlinear system is to solve one equation for one variable, and you can take your pick. Then number 2, substitute this expression in for the appropriate variable in the other equation. And then number 3, solve that resulting equation now in one variable. That resulting equation may be linear, it may be nonlinear. You'll have to diagnose the equation and apply appropriate method to solve that equation, expecting potentially more than one solution. Then number 4, back substitute the values obtained in either original equation and solve for the other variable. And then finally, number 5, express the solutions as ordered pairs, x, y, and check all answers in both original equations. So on example 3, we're going to solve the nonlinear system using the substitution method. We'll express all the solutions as ordered pairs, and then to visualize what we found, we're going to graph both equations and observe those intersection points. So we have the linear equation x plus y equals 5 and the quadratic equation y equals x squared minus 15. Notice in that second equation, y is already isolated. So I can take the expression for y and plug it into the other equation where I see the y. So substituting, we obtain the first equation, x plus the new expression for y, x squared minus 15, and that equals 5. Notice we have a single equation in a single variable. It happens to be a quadratic equation, so now we need to solve this quadratic equation. So I'm just going to rearrange the left side so that it's in descending order. And then remember, when we solve quadratic equations, either by factoring or quadratic formula, we need them equal to 0. So let's subtract 5 from both sides. That's going to give us x squared plus x minus 20 equals 0. If we factor this, we would obtain the factors x plus 5 times x minus 4 equals 0. So it looks like we have two solutions. X equals negative 5 and x equals 4. Now you want to be careful here. We did come up with two answers, but that's not the ordered pair solution of the intersection points. Those are individual distinct x values of two different intersection points. So I want to take each one of those x values and plug them back into one of the original equations to find their corresponding y values. Since y is isolated in that second equation, I'm going to use that equation to calculate y. So if x is equal to negative 5, then our y value would be negative 5 squared minus 15, or 25 minus 15, and that gives us 10. So one ordered pair solution would be x equals negative 5 and y equals 10. We'll take our second x value, if x is equal to 4, and we'll plug it into that equation. Y equals 4 squared minus 15, or 16 minus 15. Looks like our corresponding y value there is 1. So our next ordered pair would be x equals 4 and y equals 1. Now, if we take both of those ordered pairs and plug them back into both original equations, you'd quickly find that they balance both equations. But let's visualize the solution on the graph. So I want to graph both of those original equations. The first equation is a linear equation, x plus y equals 5. A really easy way to graph a linear equation in this general form is to plot the x and y intercepts. So notice, if we set x equal to 0, y would be equal to 5, and if we set y equal to 0, x would be equal to 5. You can also rewrite it in mx plus b form and use slope and y-intercept to graph it as well. So we're going to plot our x-intercept at 5, 0, and our y-intercept at 0, 5. And if you have a straight edge or a ruler, I would highly recommend using that at this point, because we want to be as accurate as possible in connecting these dots. so that our intersection points end up in the right place. All right, I did my best on that one. That's the equation x plus y equals 5. Next, we want to graph our parabola y equals x squared minus 15. So I would think about my original parent function, y equals x squared, and the 5 key points on that graph, and shift that down 15 units on the y-axis. So we can take our vertex, which originally was at 0, 0, and move it to ordered pair 0, negative 15. And then think about the other points on your parabola. I'm going to go right 1, up 1, left 1, up 1, right 2, 1, 2, 3, up 4, left 2, up 4. Do my best to make as accurate of a parabola as possible. And then we'll connect our dots. And label our curve. And remember, we predicted our intersection points would be ordered pair 4, 1. Pretty close on our graph here. And the other one was negative 5, 10. Oh, good job on that one. Negative 5 and 10. Now, you can see one of the disadvantages to trying to solve a system by graphing is you have to be extremely accurate with the way that you plot those points. So really, solving by substitution gives you an algebraically reliable solution. But we can certainly see how our solutions coordinate with the intersection points of those graphs. Let's try another example. So we have the two equations, x squared plus y squared equals 100, and x minus y equals 2. And we want to solve the system by substitution. So first we need to isolate one of the variables in one of the equations. The second equation will be easier to work with because both of those variables have an easy to work with coefficient and no exponents on the variable. So I'm just going to solve for x by adding y to both sides. And then we can take that information for x, plug it into the other equation, make sure you go to the other equation where we see the x. So replacing the x in equation 1, we have 2 plus y quantity squared, and then the rest of the equation has y squared plus y squared equals 100. So that gives us one equation in one variable. This, of course, is a quadratic equation. So we'll start by multiplying out this first set of parentheses. Be sure that you don't distribute that exponent. So to avoid that mistake, I'm just going to write that binomial twice, and then we can FOIL it out. So the first two terms have a product of 4. The outside and inside terms combine to give us 4y, and the last gives us y squared. Let's combine like terms on the next step and rewrite it in descending order. So combining these two, we have 2y squared. Next, we have 4y plus 4 equals 100. Again, because it's quadratic, it's convenient to solve it either by factoring in the quadratic formula, but both of those require it to be equal to 0. So let's subtract 100 from both sides. That's going to give me a negative 96 right here. Now notice all of those coefficients are even. So let's reduce our equation by dividing all of our terms on both sides by 2. This gives us the resulting equation, y squared plus 2y minus 48 equals 0. And then we can factor. We would factor it as y plus 8 times y minus 6 equals 0. So that's going to yield two possible solutions for y, so I'm anticipating two possible intersection points on our graph. One of our solutions is y equals negative 8, and the other one is y equals 6. Now, with that information, we need to find the corresponding y values. So I'm going to go back up to this form of equation 2, since x is isolated, and use that to find x. So I'm going to replace y in that equation with negative 8, and the corresponding x value there would be negative 6. And doing the same thing here, I'm going to replace y with 6, and our corresponding x value then would be 8. So putting those in the proper order, x first and y second, we have ordered pair -6, -8 for one of our intersection points, and ordered pair 8, 6 for the other intersection point. Now, both of those equations would balance the original equations. Another way to at least visually verify those solutions is by graphing the equations. So let's start with our first equation. We have x squared plus y squared equals 100. Hopefully you recognize that. We just learned this as a circle, right? This is a circle centered at 0, 0, and the radius is the square root of 100 or 10. So we have our center at 0, 0, and I want to measure 10 units above, below, left, and right from that center. So 10 units above, we'd have the ordered pair 0, 10. 10 units to the right, we have ordered pair 10, 0. 10 below, 0, -10. And 10 to the left, -10, 0. And then we'll do our very best to construct a circle. It's a little lopsided, but it'll do. If you want a perfect circle, again, you can use a compass to draw that. So our other equation is x minus y equals 2. If you want to rearrange it in slope-intercept form, you can certainly do that. But I think a quick, easy way in this general form is to find the x and y intercepts for the graph. So notice if y is equal to 0, x would be 2. And if x is 0, y would be -2. So it looks like that line has an x-intercept of 2, 0, and a y-intercept of 0, -2. So very carefully, if you have a straight edge, do use it. I'm going to connect the dots. And let's see how close we came to our solution. I'm going to go ahead and label my curves. X minus y is 2, and the circle was x squared plus y squared equals 100. So our predicted solutions were ordered pairs 8, 6, right on the money on that one, and -6, -8. I'm a little off on my graph on that one, so I'm just going to make a big old point there. Again, you can make it more accurate if you have a compass to construct that circle and a straight edge to graph that line. But if I'm unsure, for example, if I'm unsure about the point -6, -8, I would just test it out in each equation. So I'm going to plug -6 in for x, -8 in for y, and double check to see if I have a balanced equation. Looks like it works in the first equation. In the second equation, we had x minus y equals 2, so x minus y equals 2, and sure enough, that one works as well. So I'm a little off of my graph, but we do know that our intersection points are precise. So in this example, you can certainly see the power of algebra in generating an accurate solution, and the graph again helps us to visualize what those solutions mean.